let's do it. So here's the problem someone asked me. You want to find the equation of the tangent line to the function f of x equal to, what do I got here? 4 times secant of x at the point pi over 3 comma 8. Cool. So I will point out, because it's kind of nice, if you look at this, this already tells you what secant of pi over 3 is. Oh, shoot, there's people waiting to get in. I'll let everybody in. Okay. So if you look at this, we know that when we plug in pi over 3 for x, we get 8, meaning secant of pi over 3 has to be equal to 2. But that's one, right? If you f of pi over 3, that's 4 times secant of pi over 3. But we know that that's supposed to equal 8. So secant of pi over 3 is 2, because cosine of pi over 3 is 1/2. Not that we need to do that at all, but it is nice to kind of remind ourselves that, oh yeah, we know what's what. Okay, so we want to find the equation of the tangent line. We've got a point, we need the slope. To find the slope, we're going to take the derivative. So we're going to do the derivative just everywhere. The derivative of secant x is secant of x times tangent of x. So we're going to get 4 times secant of x times tangent of x. And then we're going to plug in pi over 3. So the slope at this point, f prime of pi over 3, is going to be 4 times secant of pi over 3 times tangent of pi over 3. Okay, pi over 3, if you don't remember, you can draw the triangle. We'll keep coming in. Good morning to everybody. So, right, here's our triangle, pi over 3. The other angle is pi over 6 with 30 degrees. And the sides of this triangle, this side is 2, this side is 1, and this side is the square root of 3. It's a good triangle to memorize if you haven't memorized it. See, 30, 60, 90 triangle, and the sides are 2, 1, and square root of 3. Biggest side opposite the biggest angle, small side opposite the smallest angle, medium side opposite the medium angle. And then cosine of pi over 3 is 1 over 2, so secant is 2 over 1. And tangent of pi over 3 is opposite over adjacent, so it's a square root of 3 over 1. So the slope here is 8 root 3. So then if we want to write the equation, I'm going to use the point slope form, so that's my preference. I'm going to say that y minus the y coordinate equals your slope times x minus the x coordinate. Now, if you want to write this in the slope-intercept form, we should distribute the 8 root 3. So we're going to get, let's see, on the right-hand side, we're going to get 8 root 3 times x, and then 8 root 3 times negative pi over 3, which is kind of terrible. So minus 8 pi root 3 over 3, and then we have to add 8. So this is your gross answer to this problem. And the thing I want to point out, the mistake I saw that the person who asked me about this problem was making was they were accidentally typing in this into WebWork. They were typing in 8 root 3x. They accidentally have the x inside the square root, which is going to be different than what we actually want. So most of the time, not most of the time, a lot of the time when people are having a problem getting the answer right, it's not because they're doing the math wrong. It's because you're putting it in WebWork in a slightly incorrect way. And WebWork is very, very picky. So just be careful. So that's how you do that problem. But yeah, WebWork, as I'm sure you are all very well, is extremely picky and not at all forgiving. So yeah, good times with WebWork and WebAssign or whatever else is good. So trig all the time, right? We are stuck with trig forever and ever and ever. All right, let's see. Where do I want to go next? Implicit with trig. Okay. Let's see. Did anyone ask me implicit one with trig? Let me be smart and mark off the problems I've got to just to make sure that I don't. Nope. Or I'll make it up myself. I feel like someone had asked me an implicit one here. Where'd you go? Oh, you're right there. Okay, cool. Let's look at this one. Yeah. No, there was another. Oh yeah. Actually, let's look. So I've got a couple implicit without trig, and then we'll just implicit with trig. So let's look at this one first, because I think this one's a little interesting. So we're given this setup. We're given that x times y is equal to 1. We are also given that dy dt is equal to -2. And we're asked dx dt is equal to what when x is equal to 2. Okay. There's a couple of ways to attack a problem like this. You could, if you wanted to, solve for y as a function of x, right? You could totally write y equals 1 over x. I don't think that's necessary, though, or really helpful, because what's being implied, hence implicit differentiation, what's being implied is that x and y are both functions of t, right? If we're writing dy dt and dx dt are things, it means y is supposed to be a function of t somewhere, and x is supposed to be a function of t. So when we differentiate this, we're going to differentiate with respect to the variable t, right? We are assuming x and y are both functions of t. If you wanted to, you could write this as, instead of writing it as x times y equal to 1, you can make it look more complicated and write it as, oh, x is a function of t times y is a function of t equals 1. These mean the same thing, it's just this is easier to write. So now we're going to differentiate both sides with respect to time. Okay, I'm going to do it over here first just to kind of show you guys what's really happening. So when I differentiate, so I'm going to use the what rule? The product rule. So I've got a function times another function. So I'm going to do the derivative of this times that plus the derivative of this times that. Right? It's always one of each thing. So the derivative of this is going to be, well, what's the derivative of x? It's the derivative of x times y plus, then we do it the other way. We leave x alone, and we times by the derivative of y, which is y prime of t, equal to the derivative of 1, which is 0. Or using maybe the more typical notation, the derivative of x is going to be the derivative of x, which is dx dt times y plus then x times, you could also say, instead of saying the derivative of y is dy dt, you could say it's, well, the derivative of y is 1, but then we're using implicit, we have to multiply by the derivative of the inside, which is dy dt, equal to the derivative of 1, which is 0. It's the same thing, just different notation. So then we're going to plug in what we know. We know that dy dt equals -2. We know that x equals 2. I feel like we don't have everything we need because we're trying to solve for dx dt, or would you prefer x prime of t? I know what dy dt is. I know what x is, but I also have to figure out what y is. How am I going to figure out what y is? Well, I've got an equation. If x is equal to 2, then 2 times y equals 1, which means y equals 1/2. So I do know what y is as well. I just have to work for it a little bit. Here's what we've got. We've got dx dt times y, which is 1/2, plus x, which is 2, times dy dt, which is -2, equals 0. Solving for dx dt, I'm going to add 4 to both sides. So I'm going to have 1/2 times dx dt equal to +4. And then multiply both sides by 2 to get dx dt equals my favorite number. It's equal to 8. 8, I don't remember what the units were for this problem, but it's going to be 8 inches per second or feet per second or whatever the units were. It might have been something totally different. I don't think I wrote it down. I did not. I will also mention, just because I think it's worth mentioning here, you could have done this the explicit way. Meaning you could have said, I'm going to solve for y as a function of, actually, I guess I'm going to solve for x as a, so it's kind of, I don't know. Yeah, it's worth doing. So if I want to find dx dt, I could solve for x as a function of y. I could totally divide both sides by y and say that x equals 1 over y, or preferably, right, if you know you're going to be differentiating something, I'd rather not use the quotient rule if I can avoid it. I'd rather say that x equals y to the negative 1 power. So now we're going to differentiate both sides, still with respect to time. So if you like, you can say that this is x as a function of time equals y as a function of time to the negative first power. Differentiate both sides. What's the derivative of x as a function of time? It's the derivative of x as a function of time. That's x prime of t, or if you prefer, dx dt. What's the derivative of some stuff to the negative first power? It's negative 1 times your stuff to the negative second power using the power rule, but then chain rule, negative 1 times your stuff to the negative second, you have to multiply by the derivative of the inside, which is y prime. Or if you prefer the other notation, it's negative y to the negative second times dy dt. And now we can plug in. We know that, I'm going to erase a little bit here. We're trying to figure out what dx dt is. We know that y is, well, we know that x is equal to 2. So again, y is equal to 1/2. So we get that dx dt is negative 1/2 to the negative second times dy dt, which is negative 2. Okay, hopefully this works out the same. It should. 1/2 to the negative second, so 1/2 to the negative 1 is 2, right? It's the reciprocal. And then 2 squared is 4. So I get negative 4 times negative 2, which is positive 8. Same answer. Yeah, that's not a bad problem. It's kind of an interesting question. Yeah. Let's look at, do I want to look at that or that? Let's go a sideways direction for a second. Someone asked me this question, which I thought was also good. I really want to emphasize the importance of making things simpler before we start differentiating, if we're being asked to differentiate. An example of this would be something like the following question. This isn't right here, sorry. Gotta keep checking things off my list. Also, yeah, there was a good question someone else asked. Sorry. Try and make sure I don't repeat myself here. Check. Okay. Someone asked this question. If I'm given g of t equals 8 over 9 t to the 4th, and I want to find g double prime. You could totally use the quotient rule here, and that would be fine, but there's an easier way to go. So I'm going to show you both ways to kind of point out how it can be easier. Using the quotient rule, so the first derivative is going to be the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, which is going to be, let's see, the derivative of 9 to the 4th is, the numbers are going to get kind of big here. It's going to be, actually, I'm going to write it in a way that's going to make it easier. I'm actually just going to write it as 9 times 4t cubed. I know that would be 36t cubed, but I know that the bottom is going to get squared. So that's going to be 9t to the 4th quantity squared. And the point I'm going to make here is, it's really, if you're going to take a second derivative especially, it's really in your interest to simplify your first derivative as much as you can before you differentiate again. So this is going to equal, let's see, I'm not going to multiply this out. I'm going to say I've got negative, right, so this is 0. That just goes away. I've got negative 8 times 9 times 4t cubed divided by, I'm going to have 9 times t to the 4th times another 9 times t to the 4th. I can cancel a 9. I can cancel a t cubed. So I'm left with negative 8 times 4, which is negative 32, over t times 9 times t to the 4th, which is 9t to the 5th. Right, that's going to make things a lot easier if we have to differentiate again. So let's take the second derivative. So taking the derivative of that, again, we could use the quotient rule. I'm going to show you guys in a second how this is really not the best way to do this, but sometimes you get stuck doing it when you're like, okay, well, I'm already there. I might do it that way. So using the second derivative, quotient rule again, it's going to be the bottom times the derivative of the top. The derivative of negative 32 is, oh yeah, that's 0. Minus the top times the derivative of the bottom. Again, I'm going to write it in a way that makes it easy to simplify. The derivative of 9t to the 5th is 9 times 5t to the 4th divided by the denominator squared. Instead of writing squared, I'm just going to write 9t to the 5th times 9t to the 5th. And now we can cancel a 9 here and a 9 here. We can cancel a t to the 4th here and a t to the 4th there. So we're left with 0 plus 32 times 5 over 9 times t to the 5th times another t, so 9t to the 6th. And 32 times 5, I'm never going to multiply by 5, but if you multiply by 10 and then divide by 2, it's the same thing. 32 times 10 is 320, divided by 2 is 160. This is 160 over 9t to the 6th. Okay, let me show you a much, much easier way to get there. If you've got a quotient and the denominator is just one term, you can rewrite this. You can write g of t, instead of as 8 over 9t to the 4th, you can write it as the coefficient 8/9, and the t can come up to the numerator or really just out to the side as t to the negative 4th. Now we can just use the power rule to differentiate this. I've got a constant times t to a power. The first derivative is 8/9 times the derivative of t to the negative 4th is negative 4 times t to the negative 6. I can multiply the negative 4 if I want and get negative 32/9. Oops, I said negative 6. I was getting ahead of myself there. Negative 4 minus 1 is negative 5. My cat seems to be losing her mind. I might have to go out there and check on her in a second. Sorry. And then, negative 32 over 9t to the negative 5th. And then we do it again. Take the second derivative. Constant multiple hangs out, so you get negative 32 over 9. The derivative of t to the negative 5th is negative 5 times t to the negative 6. And then negative 32 times negative 5 is 160. So you get 169 times t to the negative 6. Or 160 over 9t to the 6th. That's it. So the kind of lesson to be learned here is if you've got something and you've got one term in the denominator, you have to leave the constant in the denominator. I left the 9 in the denominator. But the t to the 4th of the denominator can come up out as t to the negative 4th. And then we can just use the power rule. So it's often really, really in our benefit to simplify things before we start differentiating, especially if you're going to have to take a second derivative or if you're going to have to find the critical values by setting the derivative equal to 0. So anytime you're going to have to do more than just differentiate, if you're going to have to differentiate and set it equal to 0 or differentiate and then differentiate again, it's usually a good idea to start simplifying things as early as possible. All right. Give me 1 sec. My cat is losing her mind. I'll be right back. Anyway, she's very strange. She wants to be in here, but then once I'm teaching, she's like, I don't want to be in here. Cats, you know how it is. Well, maybe you don't. But yes, you're welcome to come inside. All right. Sorry. Let me check that one off my list. Okay, let's do. We don't want to get into related just yet. Okay, I got that one. She's here. I'll show you. She's the more vocal of my two cats. See, she came in, she jumped on my chair, and now she's like, I want to leave because you're doing stuff. Fortunately, she's opening the door on her own as long as it's not fully closed. So we go now. Loud. Pain in the butt. All right. Anyway, let us look at a couple implicit problems with some trig stuff. I think I had a couple examples ready to go here. Yeah, let's look at that. So the problem with implicit, well, I don't say it's a problem, but things can get a little bit kind of complicated. So let's look at something like this. Let's do, sure, secant of y plus cosine of x times y equal to 5x squared plus y cubed. This is going to be a little bit gross, but implicit's a little bit gross sometimes. It's really the algebra that gets to be gross. So we want to find y prime or dy dx. Same difference. I usually prefer to use the y prime notation because it's just a little less frightening. So again, I should say, if you're using implicit, you've got all these x's and y's jumbled up together. We know we have to use implicit to find y prime. We can't, there's no way we can solve for y here and then differentiate. Sorry, we can't find y explicitly. We've got y implicitly. And just to kind of clarify, right, I know some teachers talk about implicit just means we're implying that y is a function of x, but we can't actually solve for y as a function of x. Whereas explicit means you can actually explicitly write y just in terms of the other variable, x usually. So we're going to differentiate. The derivative of secant of x is secant of x times tangent of x. The derivative of secant of y is secant of your stuff times tangent of your stuff times the derivative of your stuff, right? It's always the chain rule when you're talking about implicits. So the derivative here is going to be secant of y times tangent of y times the derivative of y, which is y prime. Okay, for cosine, the derivative of cosine of some stuff is negative sine of that stuff times the derivative of the stuff. Minus sine of your stuff times the derivative of x times y. So the derivative of x times y, we have to use the product rule. So the derivative of x times y is the derivative of x, which is 1, times the not derivative of y. Then we flip it. So we add, and we do the x times the derivative of y, which is y prime. Equal to, I think I have enough room here. The derivative of 5x squared is just 10x. The derivative of y cubed is 3 times my y squared times the derivative of my y. 3y squared, y prime. The rest is just algebra. I say just algebra, right? And the rest is some algebra that's kind of gross. So something to be aware of. When you're differentiating and you've got like a function of something and then the insides are like a product rule or something, it usually means we're going to have to take this part here and distribute it to each of these things, because one of these things doesn't have a y prime and one of them does. And our ultimate goal is to collect all the y primes on one side, but this piece here, you can't really, this piece kind of has y, doesn't have y and prime, it does have y prime. So you have to kind of distribute this to make sure that you break up those pieces so that you get the parts you want and the parts you don't separate. So let's see, I've got all kinds of grossness here. I've got secant of y tangent of y times y prime. Do be careful. This y prime is not inside the tangent function, right? It's fully outside. And that's always the case when you're multiplying by y prime at the end. It's always outside of whatever you've got, because it's always, right, you've got your function of your stuff, right? You're taking the derivative of that function of your stuff And then outside of it, you're always multiplying by the derivative of the stuff, which makes sense, just y prime. Same deal here, right? This 1y plus xy prime is not inside the sine function, it is outside of the sine function. I've got, I'm going to distribute sine of xy times y. You could write it like this, but it's easy to make the mistake of thinking that y is inside the sine function. Usually, we put other things in front of the sine or whatever trig function you've got. I know I didn't do it here. Usually we put y prime at the end. I don't know why, we just do. And then minus sine times xy prime is going to be minus, I'm going to write it as x times sine of xy times y prime. For some reason, we usually write the y primes at the end. Equal to 10x plus 3y squared y prime. Okay, we've got a y prime term here, and here, and here. So we're going to put all those on one side, all the other things on the other side. So I'm going to put this thing and this thing on the same side. So let's bring all the y primes to the left. I'm going to factor out as I bring it to the left. So I'm going to have a y prime factored out. We're left with a secant times a tangent, so secant of y, tangent of y. I'm going to also have a minus x times sine of xy. And then when I bring this over to the left, it's going to change sign, so it's going to be minus 3y squared y prime. But I'm factoring out the y prime, so I'm going to have a minus 3y squared. And then on the right-hand side, I'm going to have a 10x, and then add this over to get a plus y times sine of xy. Lastly, we divide by all of this garbage. So our final answer is y prime equal to 10x plus y sine of xy, y, divided by all of this. Secant of y, tangent of y, minus x sine of xy, minus 3y squared. Ooh, that is really not nice. It's not nice, but it's also, I mean, it just, I always think of these problems as a lot of like bookkeeping. You just have to make sure you're keeping track of everything, and it should be fine. It's just, there's a lot of pieces to keep track of, so we have to be extra careful. Questions about this one? Let me get out of the way so you can actually see it.
I have one question. I wanted to ask for that x sine xy. I know you moved it. I think you moved it on the other side. I just wanted to ask where that other x went, or does it stay in that equation when you factored the y prime?
Sorry, what do you mean the other x? So we're looking
Like
at
yeah, that one. I just want to like where that x went because I'm a little confused.
this x?
Yeah.
I think it stayed with it the whole time.
Oh, it did? Okay.
Right? So right, it's
Okay.
we've got x sine of xy times y prime. We have x sine of xy, and we factored out the y prime.
Oh, okay.
And then we divide both sides by all of this. So we still have the x sine of xy. So the top doesn't have the x, because that's the other piece, right? That's this piece here that went over there. But the bottom does have the x sine of xy.
Oh, okay. Okay, yeah, I see it.
Cool.
Thank you.
You're welcome. Side. Let's do one more implicit, and then we will move on to some related rates problems. So what have I got? Let's see, is there a good one here? I can just make some. Nope. Yeah. Let's find dy dx for yeah, why not? Let's do this. Tangent of y cubed plus, I don't want to be too awful, cosine of x squared, cosine, not cosine, sine of x squared equal to x cubed y to the fourth. All right, it's the same type of process. We're just differentiating everything with respect to x. So I know the derivative of tangent is secant squared of my stuff. So the tangent of y cubed is going to be secant squared of y cubed. But then we have to multiply by the derivative of the inside. The derivative of y cubed is 3y squared times y prime. Right? The derivative of some new stuff cubed is 3 times my new stuff squared times the derivative of my new stuff. Basically, the rule of thumb for implicit, assuming you're talking about y as a function of x, is whenever you differentiate something with a y in it, at the very end, you're going to have to multiply by a y prime. Derivative sine of x squared, there's no y's, great. So it's going to be derivative sine of stuff is cosine of my stuff times the derivative of that stuff, which is 2x. Times x prime if you want, but x prime is just 1, right? The derivative of x is just 1. Equal to, got to do a product rule over here. You're going to have a 3x squared times y to the fourth plus an x cubed times the derivative of y to the fourth, which is 4y cubed times y prime. Or the derivative of some stuff to the fourth is 4 times your stuff cubed times the derivative of your stuff. The rest is just algebra, meaning it's a pain in the ass, but we're going to do it. There's my y primes. Bring them all to the same side. Bring all your other stuff to the other side. So on the left, I'm going to have this minus this. And let's factor out the y prime. Because I feel like that's an easy enough step that we can do it and not have to write this a bunch of times. So I'm going to have y prime times. I'm going to rewrite the rest of this in the usual way, which would be the 3y squared part first. So we write this as 3y squared times secant squared of y cubed. Minus this, which I'm going to write as 4x cubed times y cubed. And the y prime is getting factored out. It's minus 4x cubed y cubed. We usually write coefficients or constants first, and then variables in alphabetical order, or lexicographic order if you want to say alphabetical in a mathematical way, which is dumb, but is a real word. Equal to 3x squared y to the fourth minus this, which I'm going to write as 2x times cosine of x squared. Finally, divide both sides by this giant mess to get y prime equal to 3x squared y to the fourth minus 2x cosine of x squared, all divided by this mess, 3y squared secant squared of y cubed, minus 4x cubed. How disgusting. There we go. Some good old implicit. See, I feel like people have some new pictures. I'm enjoying the new pictures. Melissa, I like the turtle. Max, I like the, I'm not sure what that is exactly. It looks kind of like, oh gosh, I can't think of the name right now. Oh well, it looks like a Halloween version of the thing I can't think of. Okay. It's like, I can't think of it. Yeah, Sanrio, exactly. I was like, it's not My Little Kitty, it's Hello Kitty. Yes, thank you. I was like, My Little Pony, Hello Kitty. Yeah, okay, My Little Kitty. That's what I'm going with. I know it's Hello Kitty. Yeah. All right, let us change directions. Well, maybe not change so much as. Oh, cool. I also have a couple of tattoos. Anyway, sorry, not important. Let's go ahead and, sorry, I had examples here. Yeah, okay, implicit. Let's do this one and that one. Oh yeah, there's that. So let's do this implicit problem first. You're given the following. You're given that, Cool. Yeah, I like, yeah. Sorry, getting distracted by the chat. So we have a cube. Cube whose edges, or sides, if you will, side lengths, whose edges are increasing at 9 centimeters per second. I guess these are, people have this problem with various numbers. 9 centimeters per second. And we're being asked how fast is the surface area changing when the side length, the edge length, is 6 centimeters and 26 centimeters. So I'll kind of, they ask us 4 specific questions, and I think they ask us the right questions, right? So the questions they ask us are in this order. What is ds dt? What is s as a function of the side length? What is half at sorry, did I write the wrong? Let me double check one thing here. Huh. I don't have that up actually. Maybe no. I think you know what I started with this. This is my own personal note. They ask this. They ask what s is as a function of L. They ask what ds dt is, and then they ask what ds dt is when you plug in L equal to 6. This is what we've been doing. It's just that, sorry. This problem, sorry. This is, so what I want to talk about is that this problem is walking you through the same process that we're talking about. It's just doing it a little bit, no, it's pretty much the same. So again, right, when we're doing this, we're trying to ask, what is changing? We know that the length is changing. And we're going to write that as dl dt, next to the variables they use. And dl dt is 9 centimeters per second. And then we also know that the surface area is changing. We don't know what that is, but we know that the way we're going to write it is what ds dt is. That's what we're trying to answer. Then we're going to write the equation relating the two things. So if you're talking about the surface area of a cube, there's 6 sides. Each side has an area of your length squared. So you're going to write that the surface area is 6 times L squared. Definitely, these related race problems really do require that we know kind of the areas and volumes of all the things. I can run through that if you guys want me to, but let me know. If you want me to talk about areas and volumes of shapes, let me know. I will. Otherwise, I'll assume you guys know them. And I'll definitely say them for each thing, but yeah. Then we're going to, so, right, we just did this part. We found S as a function of L. Cool. Then we're going to find ds dt, the derivative of S with respect to t in terms of this. So we're going to differentiate both sides. Derivative of S is the derivative of S. Derivative of 6 times L squared, well, the constant stays. 6 times the derivative of L squared is 2 times my stuff to the first times the derivative of my stuff. So that's this part of the question where they say find ds dt. And then the last part, or the last 2 parts, are to plug in your values. So they want you to find ds dt when the length is 6. So I can erase this now. Yeah. To find ds dt when the length is 6, the notation for this is often written as ds dt vertical line subscript L equal to 6. This means the derivative of s with respect to t evaluated at L equal to 6. This is going to be, let's see, I'm going to plug in, well, I'm going to write my formula. It's going to be 6 times 2, I guess I could have written 12, times L, which is 6, times dl dt, which we know is 9. Now, you don't have to write the units. You can just say them. In fact, I'm going to say them at the end first. So this is some number. It's some not nice number. It's 12 times 6 times 9. I don't know what that is. Well, should though. Sure. 216 times 3, 648, I believe. Let's check that just to be sure. 12 times 54. Yeah, 648. So what should the units be if we're talking about how the surface area is changing? And we know things are being measured in centimeters and seconds. Well, surface area should be in centimeters squared per unit of time. Right? The surface area is changing at 648 square centimeters per second. And we know that's right because, well, it's the right thing. I mean, like, right. We know it's right because we know it's right. Okay, that's a dumb thing to say. But, right, we know that this unit here, this was the length, which was 6 centimeters. And the rate of change was 9 centimeters per second. So when you multiply those together, oh yeah, you get centimeters squared per second. Again, right, if it's a length changing, it's length per time. If it's an area, it's length squared per time. If it's a volume, it's length cubed per time, or your unit cubed per time. Let's do one more example, and then I'll talk about some of the area and volume stuff. The two places in this class where area and volume equations really come up are when you're talking about related rates and when you're talking about optimization problems. So, and which are definitely coming up in the very near future. So let's do one more question, and then we'll kind of focus for a second on the volume stuff, and then we'll do a couple more, and then we'll do some increasing, decreasing, and yeah, critical values. So let's look at this other question someone asked. They were given, so most of the time with related rates problems, it's the situation where you know one thing is changing, you want to know how something else is changing, and you can write how one thing depends on the other thing only using those variables. We talked last time about how if you've got a cone, the volume of a cone is given by 1/3 pi r squared h, and typically you want to know dv dt, and you know what dh dt is, or vice versa maybe, right? But you know this one, you know one, you want to know the other one, and usually this r is a problem because you need to replace it with something that is in terms of either volume or height, usually in terms of height. So what I'm trying to say with all the words in the world is that typically with a related rates problem, you know how one thing is changing, you want to know how the other thing is changing, and you need an equation relating just those two variables. Occasionally, there's an exception to that, like this next problem. So this next problem is kind of atypical from the usual related rates setup. But here it is. So we're given the following. We're given a rectangle, and we're given that the length is increasing at 8 centimeters per second. The width is increasing at 3 centimeters per second. And we're given that the length is 40 centimeters and the width is 10 centimeters. And they want to know how fast is area increasing. Okay. So we could draw a picture. I don't think we really need to, but I'll draw it anyway. So here's our rectangle. Here's the length. Here's the width. And right, they're both getting bigger, right? This is getting bigger. This is getting bigger. Because the area is the length times width. So I'm still going to follow my usual process, even though I might not need all of it. So step one, what's changing? Well, length, width, and area. We know that the length is changing dl dt, right? It's how length is changing as time is changing. dl dt is 8 centimeters per second. We know how width is changing. Width is changing. dw dt is 3 centimeters per second. And we want to know how area is changing, right? We want to know what's dA dt. And as usual, after we've identified what we know is changing, what we want to know is changing, we're then going to try and write an equation relating the non-time variables. In this case, I mean, and again, it's usually the geometric formula, right? Not always, but a lot of the time it's like, oh yeah, we've got some geometry here. I just remember, I need to grade the quiz I gave you guys, so I will try and get that done today. Grade by grade, I mean, give you some feedback. Post solutions. So here, area is length times width. Normally, most of the time, we'd be like, oh, I've got too many variables here. I want to solve, right? You often we'd be told like the length is twice the width or something like that, and then you plug in L equals 2W to get an area equation in terms of just one other variable. It's not the case here because we know everything about the length and the width. So we're going to differentiate with respect to time. The derivative of area is the derivative of area. And we're differentiating in this step. The derivative of this product, I said the word product, it means we probably need to use the product rule. Derivative of this product is the derivative of the first thing. Derivative of L is dL dt times W plus, switch it. Leave the length alone, multiply by the derivative of W, which is the derivative of W. And then we plug in what we know, we solve for what we know. We literally know everything here. We know this, 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 and this. And we're going to get that. So I'm just going to, since I'm kind of out of space here, fine, I'll do it here. Plug it in, right? We're going to get that dA dt is equal to dL dt, which is 8 centimeters per second, times W, which is 10. Right, so notice this is centimeters per second times centimeters, which is going to be centimeters squared per second, plus L, which is 40, times dW dt, which is 3 centimeters per second. And again, it's 40 centimeters times 3 centimeters per second, so it's again centimeters squared per second. So we're going to get 80 plus 120 is going to be 200 centimeters squared per second. That's our answer. Okay. Let's go ahead. I'm going to very quickly run through the geometric formulas you should be aware of in terms of area, volume, and probably the Pythagorean theorem as well. Just so everybody knows all the things. Oh, yeah, solar triangle as well. Okay, so let's talk about all the formulas you might need to know. Again, this is going to be very quick. Let's use. So area formulas. Do I want to start? Let's just do area slash perimeter. Basically 2D shapes is what I'm trying to say. So we've got a square where the side length, call it whatever you want. I'm going to call it X. All the sides are the same length. We know that the area is X squared. We know that the perimeter is 4X. That's it. Rectangle. Call the sides. I'm going to call them X and Y. You can literally use any variables you want. Area is X times Y. Perimeter is 2X plus 2Y. Great. Circle. Radius is R. area is pi times r squared. Circumference, which is perimeter, what we call circumference for a circle, is 2 pi r. The diameter is equal to 2r. This sometimes comes up, but not super. Like usually we're not asking about the diameter. It'll be good. What other two-dimensional shapes? Triangles. So there's a couple different kinds of triangles. In general, right, we usually, for related rates, we're mostly encountering right triangles. Oh yeah, we'll do a right triangle problem. So for a right triangle, this is side A, B, and C. The perimeter is not very exciting. We usually don't ask about the perimeter, although we can. The perimeter is A plus B plus C. Not super exciting. We also know the area is 1/2 the legs multiplied together. 1/2 the base times the height. And then you could also talk about how we also know that a squared plus b squared equals c squared. Right? Pythagorean theorem does come up. Other 2D shapes. I mean, there are, of course, many other two-dimensional shapes, right? Pentagon, hexagon, septagon, deceptagon. No, that's Transformers. Dodecagon, though, is a 12-sided shape. Octagon, right? The only other thing you might encounter is a trapezoid, I suppose. Right? Sometimes a trapezoid comes up. Again, a trapezoid is any four-sided shape where two sides are parallel and the other two sides are not parallel. I know this is the most common like trapezoidal shape we all think of, but I will just tell you, right, your trapezoid, this could also be a trapezoid. Or really, this side could be oriented anyway, it just can't be parallel to that side. So for this trapezoid, if this is the height, and this is base 1 and this is base 2, then the area is the height times the average of the bases. That's always how I think of it. It's the height times the average of the bases. That's all you really ever need to know about a trapezoid, I think. So, last thing about two-dimensional shapes I want to point out is similar triangles. So these come up as well. I'm going to erase over here because I'm out of room. Right, so if you've got, and this mostly comes up when you're dealing with a cone. You got something like this. Sure, where this is A and this is B and this is X, this is Y. We can say there's lots of ways of doing it. Usually just pick whatever sides make most sense. So small side to small side. So X over A is equal to large side to large side. X plus Y over B. You can do whatever, right? You could do also X over X plus Y equals A over B. Essentially, all of these similar triangle relationships come from trig functions. Really, what I'm really saying is, okay, look at this angle here. Well, if I use tangent of this angle for these right triangles, tangent of theta is opposite over adjacent. So tangent of theta is, let's do cotangent, fine. Cotangent of theta is adjacent over opposite. Cotangent of theta is x over a. It's also x plus y over b. They have to be the same. So those are your 2D shapes. Time. Let's see. Let's do a couple examples of the 2D shapes before we talk about the 3D. We'll run through the 3D shapes, and then we'll talk about a couple examples. Because I've definitely got 2 examples I already know I want to do. And a couple of people have asked me as well. I want to so many things. Okay, so 3D shapes. There's like I think 3 or 4 I can think of. So cube. So if the side length is x, the volume is x cubed. And the surface area, which I often write as SA, but most people just write as S, is 6 times x squared. Okay? And then if you have like a parallel pipe head or a rectangular prism, like that, where this is x, this is y, and this is z, then the volume is x times y times z, and the surface area is annoyingly xy twice, yz twice, and xz twice. Basically, right, each face added together, you've got 2 of these faces, 2 of these faces, and 2 of these faces. A lot of problems with optimization, which we haven't got to yet, but a lot of problems with optimization often involve a box like this, often with an open top, meaning you get like 1 of the bottom and 2 of the right, 2 of the sides and 2 of the front and back sides, but no top. But often the base will be a square, meaning that x and y are both actually just the same variables. It's like x, and z or whatever. That's a common thing that comes up. What are the 3D shapes? We got a sphere with a radius of r. The volume is 4/3 pi r cubed, and the surface area is 4 pi r squared. Interesting fact. For a circle, the area is pi r squared, and if you take the derivative with respect to r, you get the circumference. For a sphere, the volume is 4/3 pi r cubed, and if you take the derivative with respect to r, you get the next lower dimension thing, the surface area. Only true for circles and spheres. Kind of neat. There's probably some reason for it that I'm unaware of. And then the last 2 shapes, cylinder with a height of h and a radius of r. The volume is area of the circle times the height. And the surface area, this one's always the one that's a little tricky. The surface area, well, you've got a circle on the bottom and a circle on the top. So assuming it's a closed cylinder and not like a open top cylinder where you have like, right, like you have a cup, sorry, words, by the way. Hamilton cup from seeing Hamilton with the original cast in New York. Yes, be jealous. Anyway, if you have an open top cylinder, you have a cup, but if you have a closed top cylinder, you have stuff on the top, stuff on the bottom, and stuff around the side. So it's going to be bottom area is pi r squared, top area is pi r squared. That's 2 pi r squared. And then the around part, I always like to think of as like a roll of paper towels. If you took one paper towel off and went all the way around and unfolded it, it would be a rectangle. And the rectangle would have a height of h and a length of the circumference of the circle, which is 2 pi r times h. So the surface area of a cylinder is always one that kind of people often have a hard time with. So it's always something we can figure out. And then lastly, we have a cone. And if the height of the cone is h and the radius is r, the volume is 1/3 pi r squared h. And nobody ever talks about the surface area. That's not entirely true. There was definitely a problem last quarter where somebody was, they gave you the formula for the surface area, and we had to like optimize it. But I'm sorry to hear you guys all were supposed to go and didn't get to go. That is a bummer. I do recommend watching it on Disney Plus if you haven't had the opportunity to. It's excellent. But what I'll say here is that surface area, someone's going to give you that formula if they want you to know it. So don't, I couldn't tell you what it is if I tried. Okay. So let's look at some examples. I've got 2 in mind. Yeah, let's do that one. Let's do that one. So here's an example that I always think is kind of interesting. Yeah. A 6-foot tall person walks away from a 20-foot tall streetlight at a pace of 4 feet per second. How fast is the length of their shadow increasing? When they are 20 feet away from the base of the light. Meaning, right, like their horizontal distance is 20 feet, not like their diagonal distance. So let's draw a picture. So here's the ground. Here's my street light, 20 feet tall, giving off light. This is 20 feet. And here's the person walking over here. And they're going that way. And we're casting a shadow like this. So again, when you're drawing a picture like this, it's important to label the things that are changing with variables. The person's height is not changing, it's 6 feet. The street lamp's height is not changing, it's 20 feet. But the distance from the person to the street lamp is changing, so let's call that X. And the length of the person's shadow is also changing. Let's call that Y. This is looking like a similar triangle sort of deal. But before we get there, let's start writing down the things that are changing. So what's changing? Well, I know that the length the person is from the base of the street lamp is changing. I know that X is changing. Dx dt, how much the distance from the street light's increasing, is just how fast the person is walking. Right? If you want to say how fast someone is moving, you're usually saying how fast their distance from a stationary point is changing. So the distance the person is from this stationary object is changing at 4 feet per second. I would try and draw 4 with it. I'm trying to write the word 4, so it's right, 4 feet per second. And then we're interested in knowing what dy dt is. Right, we're asking how fast is the length of their shadow increasing? Okay, now we want an equation relating x and y, similar triangles. So I'm going to pick, I know I want kind of the stuff I want on top. So I'm going to say base over height, so y over 6 equals base divided by height, x plus y over 20. Most of the time, I would differentiate both sides right away. This is an exception. I definitely recommend simplifying this before differentiating. You can cross multiply. 20y equals 6x plus 6y. And you can even bring all your y's to one side. 14y equals 6x. I definitely think it's worth doing it. Most of the time it's not. Most of the time you should just differentiate both sides using implicit differentiation. Here it's worth simplifying. So differentiate both sides. The derivative of 14y is 14 times dy dt. The derivative of 6x is 6 times dx dt, right? Remember, everything is a function of time. So when we differentiate implicitly, we always have to multiply by the derivative of your variable with respect to time. Now we're going to plug in what we know. So what do I know? Well, I know what dx dt is. It's 4 feet per second. I also know that the person is 20 feet away. So I'm going to have, let's see, 14 times dy dt, where I'm trying to solve for dy dt, equals 6 times dx dt. And dx dt is 4 feet per second. And there's nowhere to plug in the 20 feet. That happens sometimes. It specifically happens when basically the thing that's changing is a constant multiple of the other thing that's changing, which is true here. So what's interesting about this is, assuming, right, like there wasn't like any diffusion, the light traveled forever, how fast the length of someone's shadow increases only depends on how fast they're walking. It has nothing, how far you are from the light source, assuming it's still casting a shadow, has no bearing on how fast the shadow is moving. Kind of interesting. So what we end up getting here is that dy dt is equal to 6 times 4 divided by 14, which reduces to 12 over 7 feet per second. So the length of the shadow is increasing at 12/7 of a foot per second. Now I want to also point out, because this comes up sometimes. Sometimes textbooks ask, instead of how fast is the length of the shadow increasing, they instead ask how fast is the tip of the shadow moving. Which is a different question, right? Because if you're asking the first question, how fast is the length of the shadow increasing, you're just asking how fast is y changing. But if you're asking how fast is this point moving, well, you have to ask how fast it's moving in reference to a stationary point, meaning you're asking how fast this distance is changing. So what we're asking here is, what's the derivative of x plus y? The answer is that it's super easy if you've already done the first part. If you're asking how fast someone's shadow is moving, it's how fast the person's walking plus how fast the length of their shadow is increasing. So if you do the first part and say, well, I know that dy dt is 12/7 of a foot per second, then the answer to this question, well, the derivative of x plus y is literally the derivative of x plus the derivative of y, aka how fast the person's walking plus how fast the shadow is growing. That's going to be 4 feet per second plus 12/7 of a foot per second. So if someone ever asks you how fast is the tip of the shadow moving, I strongly encourage you to first answer the question, how fast is the length of the shadow increasing, and then adding on how fast they're walking. It's easier that way. 4 plus 12/7 is going to be 47 of a foot per second. But that is definitely the best way to do this type of problem. So if you ever see a shadow problem like this, make sure you really, really, really read it very carefully to make sure whether they're asking, are they asking how fast the length of the shadow is increasing or how fast the tip of the shadow is moving. Is a difference. Okay, I had another one, yeah. I don't think we're going to get to any critical values today. I do apologize for that. I always intend to get further than I get, but definitely Thursday we will talk about finding all the points where a function has its derivative either equal to 0 or undefined. Also talking about where a function is increasing or decreasing. I might be able to get one example in after this example. That sounds like a cool project, Gabriella. I'm sorry it got canceled. That's disappointing. It would be fun to hear those raps a bit. Okay, where is this example? Let me just make one up. Let's say we have, no, not that one, James. I feel like I did one like this already, but I want to change it up a little bit. Let's say, here's one that's similar to the quiz if you took it. So there's a plane flying overhead at a height of, I'm going to make something up since I don't remember the numbers. So it's flying overhead at an altitude of, let's say, 80 feet high. And it's flying at a speed of, it's going at, so plane speed is, let's say, sure, it's a toy plane. It's going at 30 feet per second. Okay. Here's the person. And what we want to know is exactly 2 seconds after the plane was directly overhead. So, right, here's the moment where it's directly overhead. Here is 2 seconds later. Question 1, how fast is the distance from me to the plane? Sure, that's me, why not? How fast is the distance from me to the plane changing? So I want to know how fast this distance is changing. So let's label the things that are changing. This distance is changing. This distance is changing. This distance staying the same. So we need to, one, write those things down. So I know that dx dt, right, the rate that x is changing at is just how fast the plane is flying. So dx dt is 30 feet per second. And I want to know what ds dt is. We write an equation relating the variables. In this case, the equation is going to be the pi phi right there, because this is a right triangle. So it's going to be 80 squared plus x squared equals s squared. Differentiate both sides. The derivative of 80 squared is 0, because 80 squared is just 6,400, and the derivative of a constant is 0. The derivative of x squared is 2x dx dt. The derivative of s squared is the same idea. It's 2s ds dt. Now we plug in what we know. I know that x is, oh, what is x? Well, let's see. I know it's however far the plane went in 2 seconds. Well, it's going at 30 feet per second, so x is 60. So I'm going to get 2 times 60 times dx dt, which is 30, equals 2 times, oh, what's s? Well, if x is 60, I have a 6, 8, 10 triangle, or really a 3, 4, 5 right triangle where every side is multiplied by 20. 3, 4, 5 times 20 is 3 times 20 is 60, 4 times 20 is 80, 5 times 20 is 100. Most of the time, when you've got right triangles, people are going to try and give you numbers where the things work out nicely. So that's going to be 100 times ds dt. And then we're going to solve for ds dt. So ds dt is looking like it's going to be, let's cancel the 2's there. And we cancel the hundreds, right? Cancel, 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 cancel. So look at ds dt is 18 feet per second. Second question, which is more interesting, I think. How fast is the angle of elevation from me to the plane changing at the same moment? Good question. We got time. Yeah, we can figure this out. I want to erase. I would love to just keep this here. So I'm going to erase this stuff. So what I want to know now is, how is theta changing, right? The angle of elevation 2 seconds after the plane is directly overhead. So it's the same idea, right? We know what's changing. We know that dx dt is still equal to 30 feet per second. But now, instead of wanting to know what ds dt is, I want to know what d theta dt is. So now, instead of needing an equation relating x and s, I need an equation relating x and theta, and preferably only those variables. So let me ask you guys, what trig function could I use that's going to give me theta and x and not s? So theta and preferably these two sides. What trig function is going to be the best? What happens when you're in the sun sometimes. You guys are like, what is he talking about? Talking about tan. Yeah, tangent. Right, tangent or even cotangent is actually probably the best one here. Let's go ahead and use tangent. So tangent of theta is 80 over x. You might see why this is not the best choice. I would really prefer to have my right. So if I take the derivative here, I'm going to have to either write it as 80x to the negative first, or right. Instead, it actually is even better to say, well, you could do this. You could multiply both sides by x, say x times tangent of theta equals 80, and then divide both sides by tangent, and say x equals 80 divided by tangent. But 1 over tangent, the reciprocal of tangent, is equal to cotangent. So the nicest way to actually do this is to say that cotangent of theta is x over 80. Or preferably, x equals 80 times cotangent of theta, which is what you would get if you rewrote this. So now let's differentiate that. The derivative of 80 times cotangent, well, that's going to be 80 times, all right, what's the derivative of cotangent? It's negative cosecant squared theta times the derivative of theta, right? We're still differentiating with respect to time. So derivative cotangent of some stuff is negative cosecant, oh, holy smokes, can I write my letters right? Negative cosecant squared of theta times d theta dt equal to the derivative of x, which is dx dt. All right, plug in what we know, solve for what we don't. I know dx dt is 30. I've got a negative 80 times cosecant squared times d theta dt. Well, I should be able to figure out what cosecant squared is, because again, I should be able to figure out everything except for the thing I'm trying to solve for, which is d theta dt. So cosecant of theta, cosecant is the reciprocal of sine. Sine of theta is opposite over hypotenuse. The hypotenuse is still equal to 100 at this moment. So sine of theta is 80 over 100. So sine of theta is 8 over 10, which is 4 over 5. Cosecant of theta is 5 over 4. This is going to be 5 over 4 squared. So then we're going to solve for d theta dt. Let's see what we've got here. We've got negative 80 times 25 over 16 times d theta dt equals to 30. So then 80 divided by 16 is 5. So you've got negative 5 times 25, which is negative 125. So negative 125 times d theta dt equals 30. And dividing by negative 125, you get d theta dt equals 30 over negative 125, or negative 30 over 125, which could reduce to negative 6 over 25. 2 points, and I know it's time. One, does it make sense that it's negative? Yes, because as the plane flies that way, if plane's like over here, the angle is going to be smaller. So the rate of change being negative makes sense because the thing we're talking about is getting smaller. Second thing, what are the units? So whenever you're doing a related rates problem, you're talking about an angle, the units are always in radians per unit of time. So radians per second. Why not degrees? Well, because we don't have a unit of degrees, right? No one said there were any degrees here. And radians are a unit without dimension, right? When you're talking about a radian, you're really talking about just the proportion of one length divided by another length, which is what we have here, right? If you take a look back at our equation just for 1 second, tangent of theta was 80 feet divided by x feet. So 80 feet times cotangent of theta equals x feet. And when you differentiate both sides, you still have 80 feet here. You have dx dt feet per second. So when you divide here, you've got feet per second divided by feet, so you just got blank per second. The blank, not having any dimension, is your radians per second. So if you're dealing with angles, the rule of thumb is just, if it's a blah, blah, words. If you're talking about angles at a rate of change, it's always radians per second or minute or hour or whatever the unit of time is.